In this problem, we'll be proving Bezout's lemma. In number theory, Bezout's lemma, also known as Bezout's identity, states that for any integers a and b with greatest common denominator d, there exists integer x and y such that ax plus by equals to d. Furthermore, the integers of the form ax plus by are exactly the multiples of d. So, to prove Bezout's lemma, we can let a equal to a0 times d and b equals to b0 times d, since d is the greatest common divisor. So here we let a equal to a0 times d and b will equal to b0 times d, where for some a0 and b0, and the GCD of a0 and b0 are going to be 1, meaning that a0 and b0 are coprime. And then we can divide ax plus by equals to d, or GCD of ab, by d. So we'll get that a0x plus b0y will equal to 1. And then, using the observation that 1 is the smallest positive integer, we can write the following proof. Let a0 and b0 be relatively prime positive integers. So, if we have a set S, we can define as a0x plus b0y for x and y belonging to integers. We have a0x plus b0y is greater than 0. Because S only contains positive integers, the well-ordering principle guarantees it has a minimum value. a0x plus b0y equals to 0 for some x, y, and d0. And here we wish to prove that d0 equals to 1, as shown here. So we want to prove that d0 divides both a0 and b0. How do we do this? Well, we can apply Euclidean division, which states that there exist integers q and r such that a0 equals to d0q plus r, for 0 is less than or equal to r is less than d0. Solving for r, we have r equals to a0 minus d0 times q. Substituting a0x plus b0y equal to 0 to d0 will yield that r equal to a0 minus a0x plus b0y times q. And r will equal to a0 times 1 minus qx plus b0 times qy. Hence, r is the form of a0x plus b0y. And note that we define r to be less than d0, then because d0 is the smallest positive integer of the form a0x plus b0y, where r must be 0. Hence, we have a0 will equal to d0 times q. And then we will have d0 divides a0 because q is an integer. And then with a similar logic, we may deduce that d0 will also divide b0. Hence, d0 divides the GCD of a0 and b0. So we have d0 will divide 1, meaning that because d0 is positive, it must be equal to 1. So we have a0x plus b0y equal to 1. Multiplying by d will give us ax plus by equal to d, or ax plus by equals to the greatest common divisor of GCD AB. And that's how you prove Bezout's lemma.